Hi everyone, we're team number 3. My name is Zishuan Zhang, a senior electrical engineering student minoring in computer science. My teammate Chen Xuan is a junior electrical engineering student. Our project is called License Plate Enhancement with Generative Adversarial Network. So there are many applications of image reconstruction. So for instance, in painting removal and image denoising. So in our case, the goal is to make plate number as legible as it can be. So why do we care? One good application of plate enhancement is for law enforcement. I'm sure you know what I'm talking about since this magic trick is frequently used in Hollywood movies. Our project can also be used to increase the accuracy of plate recognition or like classification, especially for long-range detection as an intermediary pipeline. Another important feature of the project is that it can be easily transferred to other domains, such as street name recognition for unmanned vehicles. So our project offers a way to solve these problems. So before diving into the details of our architecture, I want to show you the results we obtained. So our model can reconstruct the original image very accurately, but also blurs the plate if the ground truth is noisy. So last but not least, our model can also automatically adjust image brightness and contrast. So how did we do it? So the first step would be data extraction. We use the dataset that's called the Chinese City Parking Dataset, which consists of 400,000 images. We extracted plates from street views, such as this one, and we use some algorithm to extract the plates. The second step would be data augmentation. We filtered out bad quality images and created high quality, low quality image pairs with corrupted with random brightness, contrast, and noise. The third step is testing the performance of various state-of-the-art architectures. The fourth step is improving the visual perception of our model reconstruction using the generative adversarial network. Okay, so like any generative adversarial networks, there are two models in this project, the generator and the discriminator. The capability of the generator directly impacts the reconstruction accuracy of plate images. Therefore, we did experimentations on several state-of-the-art architectures. The rightmost column is reconstruction done by bicubic upsampling. The second rightmost column is done by ESPCN, a lightweight super resolution framework that is used as a benchmark. So as you can see, this problem is not trivial, and it takes advanced architecture to create realistic reconstructions. The main contenders here are the SRSNet and RRDBNet. So they are on par with each other in terms of peak signal noise ratio or structural similarity index. However, I say that RRDBNet creates more accurate reconstruction. For example, if you take a look at this character, it's RRDB successfully recovered it. However, SRSNet didn't. So RRDB seemed to be the right choice. So this is a detailed block diagram of RRDB, of our model, which is an enhanced version of the original RRDBNet defined in this paper. Okay, so the major modification we did is replacing the upsampling layer with what is known as subpixel convolution here. So this subpixel convolution layer converts the depths of feature maps into image height and width. So for example, if you have a 10 by 10 by 64 feature map, this layer will convert it to an 80 and 80 by 1 feature map. So it really just squashes the feature map into a flat, two-dimensional tensor. So our model also benefited a lot from what's called a local feature fusion and local residual learning defined in this paper. So because our model is extremely deep, we have like 10 RRDB blocks here, which means more than 100 layers of convolution and batch normalization. Without the residual learning, we won't be able to train a model this deep. Okay, evaluation. So one problem we encounter during training is that image reconstruction is a very subjective task. Images with the same PSNR can be perceptually very different. Later, we also figure out that not only PSNR is not a comprehensive metric, it is not a good metric at all. So if you take a look at these two pictures, the first one has significantly lower peak signal noise ratio. However, in terms of perception, it's much easier to read than the second one. So PSNR doesn't really mean good reconstruction. So to solve this problem, we use a novel loss function defined in this paper. So we also, instead of optimizing the mean square error, we also want our model to pay attention to high-level detail, high-level features such as edges, orientation, and shapes, which is quantified by the L2 norm in the feature space. So if you have two images, instead of calculating the L2 norm in the image space, we extracted the features of these two images using a VGG network and do the calculation on the feature map. So as you can see here, we have the content loss tends to create images that have like clear and evident shapes and edges, and MSE loss tend to create over smooth, cheating answers. Oops. So we also use a discriminator to constrain the possible reconstructions because the goal is to create legible numbers. We want our model to create character-like shapes instead of artifacts like what you see in the MSE-based reconstruction. Okay, so here is the network of our discriminator. Nothing exciting really, because it's just a simple VGG style network. It produces 0 if the image is fake. It produces 1 if the image is real. So during the training, it turned out that even a simple VGG-like network like this can win the min-max game very easily. So in other words, the discrimination accuracy can reach 95% very quickly, and the generator is totally ruined. So to prevent the landslide victory for the discriminator, we followed the advice of Ian Goodfellow's Neural IPS GAN tutorial. Namely, we pre-trained the generator model so that it produces very good reconstruction even before the min-max game. We used large learning rate on the generator, and certainly we optimized the discriminator loss less often. So instead of optimizing it every step, we only do so every 3 steps. Only doing so did our model finally reach a good Nash equilibrium. So the benefits of GANs. The first column is images created without GAN, and the second one is with the GAN penalty. So as you can see here, the first column tends to produce, the model trained on pure content loss tends to cheat by creating over smooth artifacts. The GAN network on the other side is constrained to output character-like shapes. So as you can see here, the GAN network tend to produce less significant artifacts than models without the GAN penalty. So we also want to talk about what didn't work in our project. So the first thing is extreme data imbalance. So because of our data set is largely collected in the same province, the model tends to reconstruct any Chinese characters encountered to the name of the province where the data set is collected. So for example, if you take a look, where's my mouse? So it basically converts every Chinese character encountered into the same Chinese character as a majority class. And second thing is that we still have a lot of room for improvement. So even with the help of GAN, our model sometimes still struggle to output any meaningful reconstruction. And the third thing is the confusion between similar shapes. So as you can see here, the model sometimes falsely convert the input image into something different. For example, instead of converting it to G, it reconstructs 6, which are very similar, these two letters. However, in our application, this can be a very serious misleading phenomenon. Okay, so this is the list of our work cited, This is the list of work cited by our project. Okay, that's it. Thank you for listening.